Welcome everyone to Unit 1, Day 2. Today we're going to find some slopes of tangents, and in this case we are finding the slope of a tangent to the curve, and the curve we have actually, if we look at it closely, is y equals x squared, and we can bring it through something like that, and we have this point P here at 3, 9. And we have this point Q somewhere else on the curve at some extra value of 3 plus h. And of course, since we're looking for slope, we are looking for y2 minus y1 all over x2 minus x1. And if we use our PQ in this case, we'll have our y2 being 3 plus h all squared minus the 9 all over 3 plus h minus 3. And we'll notice in the denominator we get just a single variable of h. And if we multiply the numerator out, we'll have 9 plus 6h plus this h squared minus 9. And we'll also notice our constants in the numerator will cancel out as well. We'll be left with 6h plus h squared all over h. And if we notice there, we have a common factor of h in that numerator and have 6 plus h all over h. And if we continue that, we of course, the h's will of course cancel quite nicely, leaving us with 6 plus h in our final result. Now of course, if we look back to our question, so there's our general slope, and it's still a general because we had that h variable in there because q can be anywhere. Now what happens? So in part B here, what we're looking at, of course, is what happens when we take the limit of h approaching 0 of this now slope, which is 6 plus h. And we're looking at what does it become. Now, of course, what this means graphically is as q gets closer and closer and closer to p. So instead of having the slope of a secant, we are, of course, getting to a slope of a tangent. And as it gets closer and closer, we're going to more closely represent that slope of that tangent. And hopefully, in this case, you can see that it's obvious going to end up being 6 for its limit. So here we go in example 2. So here we are looking at another quadratic, but let's put it all together. We don't want to just look for that general slope first. Let's, in this solution, what we're going to do is we're going to find that slope, but in essence do part B of example 1 as well. So we're looking at the limit of h approaching 0 of that general slope, which of course will be x plus h minus f of x all over x plus h minus x. And what you'll notice, of course, even in the general form, our denominator here can be simplified to just h, and there's our m. This, of course, will become our general slope formula for any slope of the tangent. So we can throw in here, we can actually put a little t underneath that slope, denoting that it is indeed a slope of a tangent. So let's look at it for this specific case. So we have f of x, so we always, of course, need our limit of h approaching 0 of our function. And let's move that red box up a little bit, make it a little bit easier to read down below. Excuse me. We will have, of course, f of x, so negative bracket x plus h all squared plus 2 times x plus h plus 6 minus, and we'll just move it over so we have a little bit more room, our f of x, which is just minus x squared plus 2x plus 6, all over, of course, h. Now, when we take the limit of h approaching 0, it's in the denominator. So that, of course, means division by 0, which we want to get rid of. So, let's do some algebra into the numerator, and hopefully when it's done, we'll have some canceling out so that we don't have our division by 0. So what are we going to have in that first term? Negative, of course, the binomial expansion will be x squared plus xh, but we've got the minus in front of it, so minus 2xh. And we'll have h squared, so again, minus h squared plus 2x plus 2h plus 6 minus, negative makes positive, so positive x squared minus 2x minus 6 all over that h. Now the beauty of this, our x squareds will cancel each other out, our 2x's will cancel each other out, and our 6's also cancel each other out. Wow, and let's see what we're left with here. So we have the limit of h approaching 0. And what are we left with in that numerator? We have a negative 2xh, a negative h squared, we have positive 2h, and that's all over h. A lot of h's there. And so let's take a common factor out of h, left with negative 2x minus an h plus 2 left over h, and lo and behold, those h's nicely cancel for us, which is really nice, because this gives us the limit of h approaching 0, bracket negative 2x minus h plus 2. Since we want to take the limit of everything, we must have the brackets here. But then as we take the h approaching 0, that middle term drops out, and we'll be left with negative 2x plus 2. So this is our general slope of the point where we want our tangency. Now if we think back to our original question, we want the x value of 5. So down in the bottom here, what we can do, of course, is at x equal to 5, this slope of the tangent now becomes negative 2 times 5 plus 2, which will give us, of course, negative 10 plus 2, or negative 8, as our slope of the tangent at the point x equals to 5. So let's look at our third example here, this time doing it with a rational function. So our solution in this case is still going to go with our new general formula. Slope of our tangent is the limit of h approaching 0 of our function at our points plus h minus the function at just our point all over h. Now with the rational function, we're still going to a nice square root function. Again, our solution will follow our slope of our tangent will equal the limit approaching 0 of our function at x plus h minus our function at f of x all over h. So in this case, doing it to a square root function, let's see what happens. So we'll end up with the square root of x minus the square root of x plus 4 all over h. Now, our dilemma, of course, is how are we going to cancel out that h? In the last two examples, the denominator's h canceled out nicely. In this case, the numerator. So, what we do, of course, is if we want to get rid of an h underneath the square root, we need to get rid of the square root sign, which means we have to rationalize our numerator in this case. So we'll multiply that numerator by its conjugate, and of course repeating it in the denominator to keep our equation the same. So what this will do, of course, is eliminate that radical in the numerator. So we're going to have the limit of h approaching 0. In this case, since we're going to multiply it through, we'll end up with x plus h plus 4, its square, of course, minus that square of x plus 4 itself, all over h times this conjugate, x plus h plus 4 minus, so plus, of course, x plus 4. And of course, if you look to that numerator, the nice part again, x's will cancel out, the 4's will cancel out, and we're left with a nice value in the numerator. Nice, of course, because it is strictly h, and look at that, it will cancel out with that h in the denominator, giving us, of course, the situation that we've had on the last couple of examples, where the h will indeed cancel out, eliminating our division by 0. And so we're left with 1 over the radical of x plus h plus 4 plus the root of x plus 4. And when we evaluate that limit, we end up with 1. And you'll notice the two terms in the denominator become the same term. So in other words, 2 of our x plus 4's radicals are h, of course, not equaling 0. And of course, we want this at x equal to 5, so if we move it up and give it a little more room. At x equal to 5, our slope of our tangent for this square root function will become 1 over 2 times the root of 5 plus 4, which of course is 9, root of 9 being 3, or 1 over 6 being our final answer. So hopefully that made a little bit of sense. So we looked at not only our new formula for our slope of our tangent, that being, of course, the slope of the tangent being the limit of h approaching 0 of our function f of x plus h minus f of x all over h. And we'll get some work on, practice on page 18 through this new formula.